Hello there, and welcome to Earth and Beyond, where curiosity gets cozy and the cosmos takes the scenic route to slumber. Tonight we drift towards something that should not exist. At least not here, not now, not moving the way it does. A visitor from beyond our sun, carrying within its frozen heart the chemical memories of a star system we will never see. Before we step into that mystery, let me ask you something simple. Where are you listening from right now? Maybe you are tucked into bed, the lights dimmed, the weight of the day finally lifting from your shoulders. Maybe you have morning coffee in hand, watching the world wake up through a window, searching for a moment of quiet before everything begins. Or maybe you are somewhere in between, a pause, a breath, a rare stillness in the turning of the ordinary hours. Wherever you are, I invite you to imagine the darkness between stars, not the darkness of closed eyes or unlit rooms, but the vast patient darkness that fills the space between suns, a darkness so complete, so ancient, that light itself becomes a rare and precious thing. If you find this sort of calm exploration soothing, I would be grateful if you gave the video a like, or maybe subscribed. It helps this quiet corner reach others who might also enjoy wandering through the strange territories where science meets wonder. Now then, let us move carefully into that world. Right now, as you settle into this moment, something extraordinary is happening in our solar system. Something that does not quite belong. An object, designated 3I Atlas by the astronomers who track such things, is racing through the space between planets at a speed that defies the gentle expectations we have for visitors from the outer dark. It is moving at 58 kilometers per second. Think about that number for a moment, not as mathematics, but as motion. If you could somehow travel at that speed, you would circle our entire Earth in just over 11 minutes. You would reach the moon from Earth in less than 2 hours. You would pass from where you sit now to the other side of the planet before you could finish a meal. This is not the leisurely drift of a comet born in our own distant sphere of icy bodies, the region astronomers call the Oort cloud, which marks the outer edge of our sun's gravitational influence. Those comets, when they fall inward toward the warmth of our star, arrive with speeds measured in tens of kilometers per second, sometimes 20, sometimes 30, rarely more. They are children of our system, bound by the same gravitational choreography that has guided their motion for billions of years. But 3I Atlas is different. Its velocity speaks of origins elsewhere, of a journey that began not in the frozen outskirts of our sun, but in the gravitational embrace of another star entirely. The story of 3I Atlas does not begin with its discovery in July of the year 2025. It begins perhaps 1 billion years ago, maybe more, maybe less. Time itself becomes uncertain when we speak of interstellar journeys. Picture, if you will, a planetary system in the process of formation, a young star still surrounded by the disk of gas and dust from which planets condense, burning bright and hot in some distant corner of our galaxy. Around that star, worlds are taking shape, sweeping up material, clearing lanes through the debris, and in that process, in the gravitational dance of forming planets, some objects are flung outward, not gently, but violently, accelerated to speeds that break the bond between them and their parent star. This is how interstellar travelers are made, not through intent, but through the chaos of planetary birth. A close encounter with a young Jupiter-sized world, a gravitational slingshot that adds velocity upon velocity, until an object once destined to become part of a comet, or perhaps the core of a small planet, finds itself instead racing away from everything it has ever known. At first, it still feels the pull of its star. The gravity weakens with distance, but it remains a fading tether. Eventually, at some threshold measured in light years, that final connection breaks. The object becomes interstellar, belonging to no star, claimed by none, drifting through the galaxy under the influence of the Milky Way's vast gravitational field. For 3I Atlas, that journey might have lasted longer than our own solar system has existed. While our sun was forming from a collapsing molecular cloud, this traveller was already adrift between the stars. While Earth was cooling from its molten birth, while the first oceans condensed, while life began its improbable experiments in chemistry. 3i Atlas was travelling through the void. It passed through regions where stars are born, skirted the edges of supernova remnants, drifted through molecular clouds so cold that even hydrogen freezes into ice. Each of these environments left its mark. Cosmic rays, high-energy particles that pervade the galaxy, bombarded its surface, breaking molecular bonds, creating new compounds, transforming simple ices into complex organic chains. Imagine the loneliness of such a journey. Not loneliness as we experience it. For 3i Atlas has no awareness, no capacity for feeling, but loneliness as a fact of existence. To be so far from any source of warmth, so removed from the gravitational architecture that gives meaning to orbital motion. For perhaps 1 billion years, the only light it knew was starlight, faint and distant, the collective glow of the galaxy itself. The only warmth was the cosmic microwave background, that fading remnant of the Big Bang, providing a temperature just 3 degrees above absolute zero. In such cold, such isolation, matter behaves in ways we struggle to replicate in laboratories. Quantum effects become macroscopic. Superfluidity becomes possible. The boundary between solid and gas blurs into something strange. But then, perhaps just a few million years ago, it's a blink in cosmic time, 3i Atlas began to bend its path, not sharply, not suddenly, but gradually, as it entered the gravitational field of our Sun. At first, that influence was subtle, barely perceptible against the broader pull of the galaxy. But as the distance closed, as millions of miles became hundreds of thousands, then tens of thousands, the Sun's gravity grew dominant. 3i Atlas, which had been travelling in what we might call a straight line through the galaxy, began to curve. Its path became a hyperbola, one of those elegant mathematical shapes that describe how objects move when they pass through a gravitational field too fast to be captured. The discovery came on a July night in the year 2025, though the exact date varies depending on which telescope you ask. The Atlas system, Asteroid Terrestrial Impact Last Alert System, a network of robotic telescopes scattered across the globe, designed to scan the sky for anything that moves, caught something moving where nothing should be. At first, it was just a streak of light in an image, a faint smudge that could have been an asteroid, a comet, or perhaps just a cosmic ray striking the camera. But when astronomers compared that image with others taken hours earlier, then days earlier, they realized something remarkable. This object was not following the predictable paths that asteroids follow. Its motion suggested an orbit that did not close, that did not loop back around the Sun. It was an orbit arriving from interstellar space, and after a brief visit, it would return there. News spread quickly through the astronomical community. Within days, telescopes around the world turned their attention toward this visitor. Every observatory that could see that patch of sky pointed its instruments in that direction. Spectrographs were deployed to analyze the light, to understand what this object was made of. Cameras tracked its position with exquisite precision, building a picture of its trajectory. And slowly, carefully, the story began to emerge. This was the third interstellar object humanity had ever detected, the third visitor from beyond, following 1i Oumuamua in 2017 and 2i Borisov in 2019. But from the very beginning, 3i Atlas revealed itself to be different. Oumuamua had been small, perhaps a few hundred meters across, tumbling through space without any sign of the activity we associate with comets. No tail, no coma, just a dark, elongated object reflecting sunlight in peculiar ways. Some called it a cosmic cigar. Others believed it a fragment of a larger body, sheared off by some ancient collision. It passed quickly, giving us only weeks to study it before it faded from view, leaving behind more questions than answers. 2i Borisov had been different, more conventionally comet-like, with a visible coma and tail, behaving just as an icy body should when warmed by our Sun. It allowed astronomers to study interstellar material in detail, to compare its composition with the comets born in our own system. The verdict was complex, similar in some ways, different in others, suggesting that while the basic chemistry of planet formation might be universal, the details vary from star to star. Now 3i Atlas was arriving, and it was bringing its own peculiarities. As astronomers gathered more observations through late July and into August, they began to notice something unusual. The object was brightening, but not in the steady, predictable way that comets typically brighten as they approach the Sun. Instead, it seemed to be awakening in stages, as if crossing invisible thresholds in space triggered different processes within its frozen heart. First, a faint haze appeared around what must be the nucleus, the solid core of the object. This coma, as astronomers call it, suggested that ices were beginning to sublimate, turning directly from solid to gas without ever becoming liquid. But the spectrum of that coma, the fingerprint of its composition written in the wavelengths of light it emitted and absorbed, revealed something unexpected. There was carbon, specifically diatomic carbon. 2 carbon atoms bonded together, glowing with a characteristic green light. That in itself was not unusual. Many comets show such emission, but the timing was wrong. 3i Atlas was still more than 2 astronomical units from the Sun, twice the distance from Earth to our star, far beyond where we normally see such strong carbon emission in comets from our own system. It was as if the faint warmth of our Sun, still distant and weak at that range, was triggering chemistry that should not yet be possible. Imagine what that means. At 2 astronomical units, the sunlight falling on 3i Atlas is only 1/4 as intense as it is on Earth. The surface temperature would be far below freezing, perhaps 150 degrees Celsius below zero. At such cold, water ice remains solid and stable. Carbon dioxide might sublimate slowly, and more exotic ices, carbon monoxide, methane, nitrogen, might begin to evaporate. But to see such strong carbon emission suggested that something else was happening. Perhaps the surface of 3i Atlas was not pure ice, but a complex mixture, possibly with a dark, insulating crust that trapped heat, allowing localized hotspots to reach temperatures where unexpected chemistry could occur. Or perhaps, and this is where the wonder deepens, perhaps the composition of 3i Atlas reflects the chemistry of its birth system. Different stars have different abundances of elements. A star richer in carbon than our Sun might produce a planetary system where carbon compounds are more abundant, where the ices that form in the outer reaches carry more organic material. When such an object is ejected and spends eons in interstellar space, bombarded by cosmic rays, those organics could transform into complex molecules that, when finally warmed by a star again, even our distant Sun, break apart to produce the carbon light we observe. As August turned to September, 3i Atlas continued to brighten, and the coma, that ghostly halo of vapour, grew more distinct. Astronomers working through the night, chasing this visitor across their telescopes' narrow fields of view, began to notice structure within that glowing haze, not just a uniform glow, but hints of jets, of streamers, of material being released in particular directions. This suggested that the nucleus was not a simple, uniform ball of ice, but a complex body, with active regions and quiet regions, with variations in composition, or perhaps in the amount of sunlight each area received as the object slowly rotated. And it was rotating. Careful measurements of how the brightness varied over time, subtle changes in the intensity of the reflected sunlight, revealed a pattern. Not fast, not tumbling as some small asteroids do, but a slow, measured spin, perhaps completing one full rotation every 8 to 10 hours. That rotation would create a pattern of day and night across the surface of 3i Atlas, and with it, a rhythmic cycle of heating and cooling. Areas facing the Sun would warm, ices would sublimate, gas would escape, areas in shadow would cool, sublimation would slow, frost might even recondense upon the surface. Over and over this cycle would repeat, day after day, as 3i Atlas drew closer to our star. By mid-September, the object was nearing 1.5 astronomical units from the Sun, roughly the distance of Mars's orbit. And that was when things began to turn truly unusual. The brightening, once steady, if somewhat faster than expected, suddenly accelerated. In only a few days, 3i Atlas became noticeably brighter, as if some hidden threshold had been crossed, some internal change awakened. Astronomers, reviewing their data, checking their instruments, found no error. The brightening was real. Something about crossing this region of space had triggered a response from 3i Atlas, a reaction far greater than the simple increase in sunlight could explain. What could cause such behaviour? One possibility is that the surface of 3i Atlas is layered, like an onion, with different ices at different depths. The outermost layer, processed by billions of years of cosmic ray bombardment, might be relatively inert, slow to sublimate. But as that layer eroded away under the sun's warmth, it could suddenly expose a deeper layer, fresh ice, untouched for eons, that vaporizes rapidly when revealed. Such an abrupt release of gas would explain the sudden brightening, and suggest that 3i Atlas is not in equilibrium, that its surface is changing, evolving, reshaping itself as it makes this first passage through the inner solar system in perhaps 1 billion years. Another possibility, more speculative but fascinating, is that the slow rotation of 3i Atlas might have brought a particularly active region into sunlight. Imagine a large deposit of volatile ice, hidden in a depression or a crater, suddenly turning to face the sun. As it warms, it releases a burst of the gas, a temporary but dramatic increase in activity. Such outbursts are seen in comets from our own system, but usually only when they come very close to the sun. To see that kind of activity at 1.5 astronomical units suggests that 3i Atlas is unusually rich in volatile material, or that its volatiles are unusually reactive. As September gave way to October, and 3i Atlas continued its inward plunge toward perihelion, its closest approach to the sun, the astronomical community prepared for a rare and extraordinary opportunity. On the 3rd of October, 3i Atlas would pass within 1/4 of an astronomical unit of Mars. Now, 1/4 of an astronomical unit is still more than 37 million kilometres, vast by human standards. But in astronomical terms it is close. Close enough that every spacecraft, every rover, every orbital observatory around Mars could potentially observe this visitor. The excitement was palpable. Mars missions are designed to study Mars, its atmosphere, its geology, its potential for life. They are not optimized for comets, but for this one event, this one interstellar traveller, mission planners began exploring how to retask their instruments. The Mars Reconnaissance Orbiter, with its high-resolution camera, might capture the nucleus itself. The MAVEN spacecraft, Mars Atmosphere and Volatile Evolution Mission, could detect if any gas from 3i Atlas drifted near Mars. Even the Curiosity and Perseverance rovers, grounded on the Martian surface beneath a thin, dusty sky, might catch a glimpse of this visitor in the faint red twilight. The trajectory of 3i Atlas through our solar system is, by itself, a quiet marvel. When plotted on a chart, when we trace its sweeping curve across the space between planets, we find something remarkable. The plane of its orbit, the invisible sheet defining its path, is tilted only about 5 degrees from the ecliptic, the flat disk where our planets travel. The probability of an interstellar object arriving with such alignment is small, not impossible, not breaking the laws of physics small, but small enough to make you pause and wonder. Is it coincidence? Perhaps. Space is vast. The galaxy holds hundreds of billions of stars. Interstellar objects are ejected constantly. Fragments flung into the dark from forming planetary systems. Most will never approach another star. They will drift endlessly, their paths shaped only by the gentle gravity of the Milky Way. But a few, a tiny fraction, will, by pure chance, pass close enough to another star to have their trajectories bent inward, to visit that system for a brief moment. And of those visitors, the ones whose paths align with the system's planetary plane are simply the ones we are most likely to detect. Our telescopes scan the ecliptic more thoroughly than the poles. Our planetary defense systems, built to find potential threats to Earth, are optimized for this flat region of space. So perhaps the alignment of 3i Atlas is not remarkable at all, but simply a selection effect, a reflection of where and how we choose to look. Or perhaps there is something more subtle at work. The heliosphere, that vast bubble carved out by our sun's wind in the interstellar medium, is not perfectly spherical. It is sculpted by the flow of interstellar gas and dust, by the magnetic fields that weave through our local region of space, objects entering this heliosphere might be gently funneled towards certain regions, much as water flowing into a drain creates patterns and vortices. If that is true, then the trajectory of 3i Atlas might carry information not just about where it came from, but about the very structure of the space it passed through to reach us. These are questions without easy answers, puzzles that will require more data, more observations, perhaps more interstellar visitors before we can speak with confidence. And that is part of the beauty. We are living in a time when the number of known interstellar objects can still be counted on one hand. Each new detection is an event, a revelation, a window into the unknown. Our grandparents lived in a world where interstellar visitors were theoretical, where the space between stars was thought to be almost empty. We live in a world where we know that space is filled with wanderers, fragments of ancient planetary systems, carrying the chemistry of distant suns across the galaxy as you rest here, perhaps feeling the pull of sleep. Consider what it means to be witnessing this. 3i Atlas is not just a distant point of light, not merely a target for telescopes or a line in a scientific paper. It is a traveller, a fragment of history, a messenger carrying information about processes and places we cannot reach. The light reflecting from its surface, the same light entering our telescopes, becoming data, left that frozen world just minutes ago. It crossed the gulf of space at light speed, carrying with it the imprint of molecules on that surface, the fingerprint of its composition. When we analyse that light, when we spread it into its component colours and measure the strength of each wavelength, we are, in a real sense, touching 3i Atlas. Not physically, but informationally, connecting to something that began its journey around another star. The warmth you feel now, if you are somewhere comfortable, comes ultimately from our sun. The light outside your window, if it is daytime where you are, is sunlight. Photons that left the sun 8 minutes ago, travelling through space to illuminate your world. 3i Atlas too is feeling that same sunlight, but at a different distance, with different intensity. As it draws closer to perihelion, its closest point to the sun, on the 31st of October, that sunlight will intensify. The surface temperature will rise, more ice will sublimate, the coma will grow larger, brighter, and we will watch, instruments trained on this visitor, gathering every photon we can, learning what we can before 3i Atlas, having made its closest approach, begins the long return, accelerating away from our sun, back toward the dark between stars. There is something profoundly moving about this, about the fact that 3i Atlas will not stay. It is not captured by our sun's gravity. Its velocity is too great, its trajectory too steep. It will leave, and when it does, it will carry with it the marks of this brief encounter. Its surface will be changed, reshaped by months of solar heating. Some of its ice will be gone, lost to space. Dust once buried deep will now coat the exterior. If 3i Atlas holds organic compounds, complex molecules forged in another system, those will have been altered by ultraviolet light, by heat, by the plasma winds of the inner solar system. In a way, we will have touched it, changed it, even though we never reached it, and it will carry those changes back into interstellar space, into regions where the sun is just another star, faint and remote. Perhaps in another billion years it will pass near yet another star, and in that encounter, astronomers around that distant world, if such beings exist, if there are minds that wonder, might detect it. They might study its spectrum, puzzle over the chemistry written on its surface, and ask whether that chemistry tells the story of previous encounters with other suns. This is the web we're part of, the slow exchange of material and information across the galaxy. It happens not through intent, but through the patient workings of gravity and time, and we are privileged, uniquely privileged in human history, to be aware of it. To track these travellers, to measure their properties, to place them within the grand context of planet formation, stellar evolution, and the living structure of the galaxy itself. We have drifted alongside 3i Atlas for a while now, watching as this visitor from beyond brightens in ways that surprised every astronomer who followed it. But now, As you settle deeper into this cosmic meditation, we arrive at something that should not be possible. Something that, when first observed, made scientists question their data, check their instruments, and finally accept that 3i Atlas was behaving unlike anything in the catalogue of known comets. Perhaps you are feeling the weight of comfort now, the gentle pull of sleep beginning to take hold. Let it happen naturally. There is no rush here. We have all the time we need to explore this mystery together. And mystery is the right word, because what comes next defies conventional understanding in ways both subtle and profound. Throughout July and August of the year 2025, as more telescopes turned their gaze toward 3i Atlas, as more photons from its surface were captured and analysed, a peculiar feature began to emerge. At first, it was uncertain, ambiguous, perhaps a trick of perspective or image processing. But as the observations accumulated from different telescopes, at different latitudes, under different skies, the feature became undeniable. 3i Atlas was producing what astronomers call an anti-tail. Now, that might sound ordinary. Comets have tails, after all. But this is different. Every comet we have ever studied, every single one, across the entire history of observation, produces tails that point away from the sun. It is not just a common pattern, it is a law of physics, dictated by how sunlight and the solar wind push gas and dust through space. Think about it for a moment. When sunlight strikes dust particles released by a comet, it exerts a tiny pressure, pushing those particles away from the sun. When the solar wind, that stream of charged particles flowing outward from our star, encounters the ionized gas in a comet's coma, it drags that gas along, creating the ion tail that points directly away from the sun. These are forces we understand, forces we can calculate with precision. The direction is always the same, away from the sun, always, except for 3i Atlas. The images showed, unmistakably, a stream of material extending from the comet toward the sun. Not a faint secondary feature, not an optical illusion created by our viewing angle, but a distinct structure, captured by multiple telescopes persisting over multiple nights. An anti-tail, material moving, or at least appearing to move, against the forces that should push it away. Let me paint you a picture of what this means in terms of probability. When we observe natural phenomena, we expect them to follow patterns, to obey the laws of physics as we understand them. Deviations from those patterns can happen, but they are rare, and when they do occur, there is usually an explanation that fits within our existing framework. The appearance of an anti-tail in a comet is not impossible, but it requires very specific conditions. Dust particles in certain size ranges, under certain illumination geometries, can sometimes appear to point sunward because of projection effects, because we are seeing a three-dimensional structure projected onto a two-dimensional sky. But the anti-tail of 3i Atlas persisted across different viewing geometries, across different phases of its approach. The probability of this being purely a projection effect, a trick of perspective, is less than 1%. Less than 1 in 100. That's the first deviation from expectation. The first indication that something unusual is happening. As you rest there, imagine what this looked like to the astronomers studying it. Picture a small, dedicated group of researchers, perhaps in observatories scattered across different continents, comparing their data in the late-night video calls, each one seeing the same impossible structure. The reaction would not have been immediate acceptance. Science does not work that way. First, there would be doubt. Check the calibration. Check the software that processes the images. Look for artifacts, for cosmic rays, for anything that could explain away the anomaly. But each check would come back clean. The anti-tail was real, present in the data with a clarity that could not be dismissed. What could cause such a thing? One possibility, explored in recent theoretical work, involves the physics of dusty plasma environments. When dust particles in a comet's coma become electrically charged, as they inevitably do in the intense ultraviolet light near the sun, they begin to interact with magnetic fields. The solar wind carries with it the sun's magnetic field, and that field can become twisted, tangled, as it flows around the obstacle that a comet represents. In certain configurations, charged dust grains might be channeled along magnetic field lines in directions that locally oppose the overall outward flow. This is complex physics, the kind that requires computer simulations to fully understand, but it offers a natural explanation for what we see. Another possibility is that the anti-tail is not truly moving toward the sun, but is instead a structure that appears to point sunward because of the distribution of dust sizes. Larger dust particles, less affected by radiation pressure, follow orbits that lag behind the comet. Smaller particles are pushed away more efficiently. The boundary between these populations under certain lighting conditions might create the appearance of a sunward-pointing structure. This too is within the realm of known physics, though it requires a specific set of circumstances to occur. But here is where the numbers begin to accumulate in unsettling ways. The probability of the anti-tail being an artifact of viewing geometry, less than 1%. The probability of 3i Atlas's trajectory being aligned to within 5 degrees of the ecliptic plane, about 0.2%. Already we're dealing with a combination of unlikely events, and we have only begun to examine the anomalies. The spectroscopic analysis of 3i Atlas, the careful measurement of which wavelengths of light it emits and absorbs, revealed another surprise. The ratio of nickel to iron in the gas surrounding the comet was inverted from what we see in natural cometary bodies, much more nickel than iron. Now both elements are present in comets. They are present in asteroids, in planets, in the dust between stars. They are, after all, products of stellar nuclear synthesis, forged in the hearts of dying stars and scattered through the galaxy when those stars explode. But the ratio, the relative abundance of nickel to iron, follows predictable patterns based on how planetary systems form. In our solar system, in the comets and asteroids we have studied, iron is more abundant than nickel by a consistent factor. This reflects the composition of the molecular cloud from which our sun formed, and more broadly it reflects the typical output of supernovae, the stellar explosions that created these heavy elements in the first place. To see that ratio inverted to find more nickel than iron suggests one of two things. Either 3i Atlas formed in a system with a very unusual chemical composition, a system born from a molecular cloud enriched by a rare type of supernova, or the surface of 3i Atlas has been altered by processes that preferentially removed iron or added nickel. The probability of such an inverted ratio occurring naturally, based on our understanding of stellar and planetary chemistry, is estimated at less than 1%. Another unlikely event, another deviation from expectation, and when we start to multiply these probabilities together, when we consider the joint probability of all these anomalies occurring in the same object, the numbers become very small indeed. Consider the rotation of 3i Atlas. Measurements of how its brightness varies over time suggest a rotation period that is unusually slow and unusually stable. Most small bodies in space, asteroids and comet nuclei, tumble chaotically, their rotation rates changing over time due to outgassing torques, and the subtle effects of solar heating. But 3i Atlas appears to rotate in a measured way, almost as if its spin has been stabilized by some internal structure or mass distribution. The probability of this, given typical formation mechanisms for comets, is difficult to quantify precisely, but it adds to the growing list of peculiarities. Then there is the composition of the coma itself. Beyond the nickel to iron anomaly, beyond the unexpected carbon dimer emission at large distances from the sun, spectroscopic observations have detected molecules that are rare in comets from our solar system. The exact details are still being analysed, but preliminary reports suggest elevated abundances of certain organic molecules, compounds that could form in interstellar space under the influence of cosmic radiation, but are typically destroyed or altered when comets from our own system undergo processing in the solar wind. Perhaps you're wondering at this point what all these numbers mean, what it signifies to have probability after probability stacking up in this way. Let me offer an analogy. Imagine you are walking through a forest, and you come across a clearing. In the centre of that clearing is a stone, and on that stone are markings. At first the markings seem random, just cracks and weathering. But then you notice that one marking looks almost like a letter. Still, you think, coincidence. Natural processes can create patterns. But then you see another marking that resembles another letter, and another. The probability of each individual marking being a coincidence might be 10%, 20%. But the probability of all of them together forming something recognizable, that probability shrinks with each additional marking. This is where we find ourselves with 3i Atlas. Each anomaly individually might be explainable, might fall within the range of natural variation, but together they create a pattern that demands attention. The joint probability, the likelihood that all of these features would occur together by pure chance in a single interstellar object, is estimated, and this is where the numbers become almost abstract, at less than 1 in 10 quadrillion. 1 in 10 quadrillion. Let that number rest in your mind for a moment, not as a call to alarm, but as an invitation to wonder. 1 in 10 quadrillion. To put that in perspective, your chances of being struck by lightning in your lifetime are about 1 in 15,000. Your odds of winning a major lottery jackpot are roughly 1 in 300 million. But the probability that 3i Atlas is displaying all of its unusual characteristics by pure chance, 1 in 10 quadrillion. This is not a number that suggests impossibility. The universe is vast, and rare events do occur, but it is a number that suggests we should pay careful attention, that we should consider all possibilities, including those that stretch our conventional frameworks. Now, as you drift deeper into this exploration, perhaps hovering on that edge between waking and sleep, let's consider what these anomalies might mean. One interpretation, the most conservative, is that 3i Atlas simply represents a type of interstellar object we have not encountered before. The sample size is small after all, for 3 confirmed interstellar visitors in human history. It is entirely possible that the diversity of such objects is greater than we imagined, that each new detection will reveal new surprises, perhaps systems around other types of stars richer in certain elements, produce comets with unusual compositions. Perhaps the processing that occurs during billions of years of interstellar travel creates surface properties we have not anticipated. Another interpretation, more speculative but worth considering, is that some of the anomalies arise from the specific history of 3i Atlas. Recent work using data from the Gaia Space Telescope, which has precisely measured the positions and motions of millions of stars in our galaxy, has attempted to trace 3i Atlas's trajectory backward in time to identify potential parent systems. The results are ambiguous. There are candidate stars, systems that 3i Atlas might have passed near in the distant past, but none that stand out as a clear origin. The uncertainties in both the trajectory of 3i Atlas and the motions of the stars are too large to make definitive statements. But one thing these studies have revealed is that 3i Atlas likely did encounter several stellar systems during its journey. Each encounter would have been distant, perhaps measured in tens of thousands of astronomical units, but close enough for the star's gravity to slightly alter 3i Atlas's trajectory, close enough for the star's wind and radiation to interact with its surface. These interactions, accumulated over billions of years, might have contributed to the unusual properties we observe now. It is a reminder that interstellar space is not empty, not completely. It is filled with stellar winds, with magnetic fields, with the slowly drifting matter ejected by stars and supernovae. An object travelling through that environment for eons would bear the marks of those encounters. There is, of course, another interpretation, one that is mentioned more often in public discourse than in scientific papers, but which deserves acknowledgement, if only because the numbers we have discussed make it impossible to completely ignore. The possibility that some of the anomalies we observe in 3i Atlas are not natural, that they arise from processes or structures that are in some way artificial. This is not a claim. It is not even a strong hypothesis. It is a question framed by the recognition that when the joint probability of natural explanations becomes sufficiently small, we have a responsibility to consider alternatives, no matter how extraordinary they might seem. The scientific method does not exclude such considerations a priori. What it demands is evidence, testable predictions, and a willingness to follow the data wherever it leads. For 3i Atlas, the data is still accumulating. The observations continue, and the interpretation remains open, subject to revision as we learn more. This is how science works at the frontier, in the space between what we know and what we are trying to understand. It is uncomfortable, marked by uncertainty and debate, but it is also where the most profound discoveries are made. As you rest here, perhaps feeling the boundaries of wakefulness soften, consider how remarkable it is that we can even ask these questions. A century ago, the existence of other planetary systems was purely speculative. 50 years ago, the idea of detecting interstellar objects passing through our solar system was theoretical, something that might happen if we built sensitive enough telescopes and watched long enough. Today we have detected 3 such objects. We have measured their properties, analysed their compositions, traced their trajectories. We are living in the opening chapter of interstellar astronomy, the era when humanity first begins to sample material from other stellar systems, to compare what exists there with what exists here. The green glow of 3I Atlas, that characteristic emission from carbon dimer molecules, speaks to the universality of chemistry. Carbon, that element so central to life as we know it, exists throughout the galaxy. It is forged in stars scattered by supernovae, incorporated into planetary systems. When it is released from the frozen surface of an interstellar visitor and excited by sunlight, it glows green, the same green we see in comets born in our own system. There is a unity here, a reminder that the laws of physics and chemistry are the same everywhere, that the universe is fundamentally comprehensible, even when it surprises us. But comprehensibility does not mean simplicity. The universe is layered, complex, filled with processes that operate on scales from the quantum to the cosmic, on time scales from fractions of a second to billions of years. When we observe something like 3I Atlas, we are seeing the integrated result of all those processes, the cumulative effect of a billion-year journey through the galaxy. To untangle that, to understand which features arise from formation, which from processing in interstellar space, which from the current encounter with our Sun, requires patience, careful observation, and a willingness to sit with uncertainty. The anti-tale continues to puzzle researchers. Additional observations, particularly those made from locations with different viewing geometries, have confirmed that it is not simply an artifact of perspective. Models have been constructed, simulations run, exploring whether known physics can account for what we see. The answer seems to be yes, but only under specific conditions. The dust must be of a particular size distribution. The magnetic field geometry must be just so. The rotation of the nucleus must align in a particular way. Each requirement individually is plausible, but together they define a narrow window of possibilities. This is often how science works. We observe something unusual, and we construct models to explain it. If the models require too many free parameters, too many specific assumptions, we begin to suspect that we are missing something, that there is a simpler explanation we have not yet found. But we do not leap to extraordinary explanations without exhausting ordinary ones first. This is not closed-mindedness. It is discipline. The recognition that the simplest explanation that fits the data is usually correct, and that our intuitions about what is simple or complex can be misleading. So we watch, and we wait, and we gather more data. 3I Atlas continues its journey through our solar system, approaching perihelion, that point of closest approach to the Sun. The brightening continues, the coma expands, new spectroscopic features emerge. Each observation adds a piece to the puzzle, constrains the possibilities, guides the next round of modelling. This is the patient work of astronomy, the slow accumulation of photons and insights, the building of understanding one measurement at a time. And through it all, there is wonder. Wonder at the fact that we can observe this at all, that the universe has arranged itself in such a way that intelligent beings on one small world can detect and analyse a visitor from another stellar system. Wonder at the complexity revealed with each new observation, the layers upon layers of physics and chemistry operating simultaneously. Wonder at the questions that remain unanswered, the mysteries that persist despite our best efforts to understand. As you drift now, carried perhaps towards sleep, let these thoughts settle gently. The universe is speaking to us through objects like 3I Atlas, telling us about the diversity of planetary systems, about the processes that shape matter over cosmic timescales, about the connections between stars. We are learning to listen, to translate the language of photons and spectra into knowledge. It is a slow process, marked by setbacks and surprises, but it is a process that reveals the universe to be richer, stranger, more intricate than we imagined. The anomalies of 3i Atlas remain for now as invitations to deeper understanding. They push at the edges of our knowledge, challenge our assumptions, force us to consider new possibilities, and in that pushing, in that challenge, there is a kind of gift, the gift of mystery, of questions that matter, of a universe that refuses to be simple or easily categorized. Tomorrow, when you wake, 3i Atlas will still be there, still racing through our solar system, still carrying its secrets, and we will still be watching, still learning, still marveling at what we find. We have travelled alongside 3i Atlas through discovery and anomaly, through the mounting questions that each observation brings. Now, as you rest in whatever quiet space holds you, we turn our attention to something more fundamental, more intimate in a way. The question of what 3i Atlas is made of, not just in the abstract sense of chemical composition, but in the deeper sense of how matter from another stellar system differs from the matter we know, how the processes of formation and transformation write themselves into the very structure of this visitor. Perhaps you're settling deeper now into comfort, into that gentle state where thoughts can drift without urgency. That's good. Let them drift. We have time to explore these layers carefully, to understand not just what we observe, but what those observations might mean. When light interacts with matter, it does so in ways that depend intimately on the structure of that matter. The size of particles, their shape, their composition, the way they clump together or remain separate, all of this affects how light is scattered, absorbed and reflected. For centuries, astronomers have used this fact to probe the nature of distant objects, to infer properties of things they could never touch directly. And with 3i Atlas, this technique has revealed something extraordinary, something that has never been seen before in any asteroid or comet, including the 2 previous interstellar visitors. The technique is called polarimetry. When unpolarized light whose waves vibrate in all directions, scatters off particles, it tends to become partially polarized, with the waves vibrating preferentially in certain directions. The degree of polarization and how it changes with the angle between the sun, the object, and the observer tells us about the size and nature of the particles doing the scattering. It's a subtle effect, requiring careful measurements, but it provides information that cannot be obtained any other way. In late summer and early autumn of 2025, several observatories turned their polarimeters toward 3i Atlas. These are specialized instruments, not common, not easy to use, but capable of measuring the polarization of light with exquisite precision. The observations were made at different phase angles, that is, different geometric configurations of Sun, Comet and Earth, building up a picture of how the polarization varies as those angles change. What they found was unprecedented. At small phase angles, when we are looking at 3i Atlas with the Sun almost behind us, the polarization is negative. This is not unusual. Many objects show negative polarization at small angles, a phenomenon related to how light scatters from rough surfaces and particle aggregates. But the depth of the negative polarization in 3i Atlas is extreme. At a phase angle of about 7 degrees, the polarization reaches negative 2.7%. To understand what that means, consider that most asteroids show minimum polarizations around negative 0.5 to negative 1.5%. A few, those with particularly unusual surfaces, might reach negative 2%, but negative 2.7% is beyond anything in the catalogue of solar system objects. Moreover, the negative polarization branch, the range of phase angles over which the polarization remains negative, is narrow, reaching an inversion angle of only 17 degrees. Beyond that, the polarization becomes positive, as expected from standard scattering theory. But the combination of a deep, narrow negative branch with such a specific inversion angle is, quite simply, unique. No asteroid, no comet from our solar system shows this pattern. Even 2I Borisov, the previous interstellar comet, displayed more conventional polarimetric behaviour. What does this tell us? The polarization signature of 3I Atlas is consistent with a surface covered in particles that are both small and highly irregular, perhaps fluffy, aggregates of even tinier grains, arranged in ways that maximise the coherent backscattering of light. This is the kind of structure you might expect from material that has been processed by cosmic rays over immense timescales, where individual grains are welded together by radiation damage into complex fractal-like structures. It suggests a surface that is ancient, not just in terms of age, but in terms of exposure, material that has been sitting in interstellar space, unshielded by any atmosphere or magnetic field, subjected to the full intensity of galactic cosmic radiation for perhaps 1 billion years. Imagine, if you will, a single grain of ice and dust on the surface of 3I Atlas. It is perhaps 1/10 of a millimetre across, barely visible to the unaided eye, if you could somehow stand on that surface and look closely. But within that grain is a history written in atomic displacements, in chemical bonds broken and reformed, in isotopic ratios altered by nuclear reactions induced by cosmic ray impacts. Each high-energy proton that strikes creates a cascade of secondary particles, a miniature shower of radiation that propagates through the ice, breaking molecules, ionizing atoms, creating free radicals that wander through the frozen matrix until they encounter something to react with. Over 1 billion years, the cumulative dose of radiation becomes staggering. Every atom in the surface layers has been displaced, possibly multiple times. Simple molecules like water, methane, carbon dioxide, these have been broken down and rebuilt into more complex forms. Long-chain organic molecules, polymers, even pre-biological structures might form in this environment. Chemistry that could never occur in the warmth and pressure of a planetary surface, but which becomes possible in the cold, radiation-rich void between stars. The surface of 3I Atlas is not pristine ice. It is processed material, a kind of cosmic rind, transformed by time and energy into something that has no analogue in our solar system. This interpretation finds support in another set of observations, those tracking the colour of 3I Atlas as it approached the Sun. Colour, in astronomical terms, refers to the ratio of brightness at different wavelengths. An object that reflects more red light than blue light is said to be red, and vice versa. The colour of a comet can tell us about the composition of its surface, about the presence of organic materials, about the size, distribution of the dust particles it releases, and 3I Atlas, once again, has shown behaviour that stands out. Early observations, made in late March and early April, showed 3I Atlas to be distinctly red. With a colour index, the difference in brightness between cyan and orange filters, of about 0.7 magnitudes. This is redder than typical comets from our solar system, and it suggested the presence of organic rich material on the surface, possibly complex tholins, those reddish-brown compounds that form when simple molecules are irradiated in cold environments. This redness was consistent with the polarimetric signature, with the idea of an ancient processed surface. But then, something changed. As 3I Atlas crossed into the inner solar system, drawing closer to the Sun, its colour began to shift. Over the span of just a few days in late April, the colour index dropped from 0.7 to about 0.3, a transition from red to nearly solar-like, meaning that 3I Atlas was reflecting sunlight in proportions similar to the Sun's own light. This change coincided precisely with the appearance of the anti-solar tail, that mysterious structure pointing toward the Sun that we discussed earlier. It was as if crossing some threshold, some distance from the Sun or some temperature, triggered a fundamental change in the nature of 3I Atlas's surface. One interpretation is that the red colour came from an outer layer of irradiated organics, a crust built up over billions of years of interstellar exposure. As the Sun's warmth penetrated this crust, as internal pressures from sublimating ices built up beneath it, the crust began to crack and shed, revealing fresher material underneath. This fresher material, still icy but less processed, would reflect light differently, accounting for the colour change. The timing coincident with the appearance of enhanced activity supports this picture. We might be watching the outer skin of 3I Atlas peel away, layer by layer, exposing the interior for the first time since it left its birth system. Another possibility, more speculative, is that the colour change reflects a change in the type of material being released. Perhaps the early activity, driven by the sublimation of super-volatile ices like carbon monoxide or nitrogen, lofted small, organic-rich dust grains that scattered light in red wavelengths. But as the comet drew closer and water ice began to sublimate in significant quantities, the character of the dust changed. Water ice sublimation can lift larger particles, and it can also produce ice grains, small crystals of water ice that are optically bright and reflect light in a more neutral way. If the coma of 3I Atlas shifted from being dominated by small organic grains to being dominated by larger, brighter ice particles, that would explain the colour change we observe. These are testable ideas, hypotheses that can be refined as more data becomes available. Spectroscopic observations, which measure not just the overall colour but the detailed fingerprint of which molecules are present, have begun to constrain the possibilities. The presence of C2, that diatomic carbon we discussed earlier, suggests organic chemistry. Hints of cyanogen, CN, another carbon-bearing molecule, add to that picture. But the absence of strong water signatures in the early observations, despite the obvious presence of a coma, suggests that water ice, if present, was deeply buried or somehow inhibited from sublimating. This brings us to one of the deeper mysteries of 3I Atlas, the question of its internal structure. When comets from our solar system are studied in detail, we find that they are not uniform spheres of ice. They are heterogeneous, lumpy, with variations in composition from place to place, layers of different materials reflecting different epochs of formation, or different regions of the protoplanetary disk from which they accreted. Some regions are rich in volatile ices, sublimating readily when warmed. Other regions are more refractory, containing dust and less volatile compounds that resist sublimation. For 3I Atlas, formed around a different star, subjected to a different history, the internal structure might be even more complex. Perhaps the layering we infer, the transition from a red, organic-rich crust to a brighter, icier interior, reflects not just processing in interstellar space, but also the conditions under which it originally formed. Different stars have different luminosities, different spectra, different winds. A planetary system forming around a star cooler than our Sun might produce comets with different volatile inventories. A system around a star richer in heavy elements might produce comets with more complex organic chemistry baked in from the start. There's a beauty in this uncertainty. A recognition that each interstellar visitor carries information not just about processes we can observe, but about environments we can only imagine. When we study 3I Atlas, we are, in a sense, engaging in comparative planetology at the most fundamental level. We are asking, how do other stellar systems make comets? How does the chemistry of planet formation vary from star to star? And what can those variations tell us about the range of environments that might exist throughout the galaxy? As you rest here, perhaps feeling the gentle pull of sleep beginning to assert itself, let your mind rest on that question. Somewhere out there, around a star whose light has not yet reached us, there are planets, moons, asteroids, comets. Some might resemble the worlds of our solar system. Others might be utterly alien, shaped by conditions we can barely conceive. And occasionally, through the patient working of gravity, one of those objects is flung free, sent on a journey through the galaxy that might, after eons, bring it within range of our telescopes. When that happens, we are given a gift, a sample delivered across light years, telling us about places we cannot visit. The polarimetric signature of 3I Atlas, that deep negative branch and narrow inversion angle, has been compared to the signatures of a few objects in our own solar system. Certain trans-Neptunian objects and centaurs, icy bodies that orbit in the outer reaches beyond Neptune. These objects too show unusual polarization properties, possibly because their surfaces have been modified by radiation over long timescales, or because they contain exotic ices not common in the inner solar system. The similarity is tantalizing, but not conclusive. It suggests that whatever processes shape the surface of 3i Atlas might not be entirely unique, that there might be analogues closer to home that we can study in more detail. But there are also differences. The colour transition observed in 3i Atlas, that shift from red to solar-like, has not been documented in any trans-Neptunian object. Those bodies are too distant, too cold, for such transitions to occur. They remain frozen, inert, their surfaces unchanging over the timescales of human observation. 3i Atlas, by contrast, is dynamic, evolving before our eyes as the sun's warmth triggers processes that have lain dormant for billions of years. We are watching an interstellar object reactivate, and in that reactivation, we are seeing clues about its composition and history that would remain hidden if it stayed cold and dark. The spectroscopic data, though still incomplete, has begun to reveal other details. The strength of certain emission lines, the spectral signatures of specific molecules, varies over time in ways that suggest rotation of the nucleus. As different regions of the surface rotate into sunlight, they release different amounts of gas, producing variations in the brightness and composition of the coma. This is expected behaviour, seen in many comets, but the details are informative. If we can map out how the emission varies with rotational phase, we can begin to infer where the active regions are located, whether they are concentrated near the equator or the poles, whether they are small localized jets or broad areas of uniform activity. One particularly intriguing observation involves the hydrogen emission from 3i Atlas, detected in ultraviolet wavelengths by space-based telescopes. Hydrogen emission comes from the dissociation of water molecules, when water ice sublimates and the vapour meets the ultraviolet light from the sun. The water molecules break apart, releasing hydrogen atoms that glow, softly, in ultraviolet light. The rate of hydrogen emission, therefore, tells us about the rate of water sublimation. And for 3i Atlas, the hydrogen emission has been surprisingly strong, given the lack of strong water signatures in the visible spectrum. This suggests that water is present and actively sublimating, but that the water vapour is being destroyed or ionised very quickly before it can build up to detectable levels in the visible part of the spectrum. Why might this be? One possibility is that 3i Atlas is producing a lot of dust along with its gas, and that dust is absorbing or scattering the visible light from water molecules, making them hard to detect. Another possibility is that the water vapour is being ionised very efficiently, perhaps because the coma of 3i Atlas has an unusual structure, or because the solar wind is interacting with it in unexpected ways. A third possibility, more speculative, is that the water on 3i Atlas is somehow different from the water in solar system comets. Perhaps deuterium enriched, perhaps contaminated with other molecules that alter its spectroscopic signature. These are questions that can be answered in principle with more observations. High-resolution spectroscopy, observations at multiple wavelengths, coordinated campaigns that track 3i Atlas over time. All of these will help to untangle the complexities. But for now, we sit with the data we have, with the hints and clues and partial answers, piecing together a picture that is still incomplete but already fascinating. There's a lesson in that perhaps about the nature of knowledge itself. We live in an age where information is abundant, where answers to most questions are just a search away. But the frontiers of science, the places where we are genuinely learning something new, are characterized by uncertainty, by ambiguity, by the recognition that we do not yet have all the pieces. This can be frustrating, but it can also be liberating. It means that the story is not yet written, that the universe still has surprises to reveal, that there is room for discovery. As you drift now, carried perhaps toward the edge of sleep, consider the polarized light from 3i Atlas. Photons that left its surface minutes ago traveled through space, passed through our atmosphere, and entered a telescope where they were measured with care. Those photons carry information, encoded in their direction of vibration, about the particles they last interacted with, and from that information we infer structure, composition, history. It is an indirect process full of assumptions and models, but it connects us to something real, something tangible, even if we will never touch it. The surface of 3i Atlas, that ancient processed rind of ice and organics, is changing even as we observe it. The sun's warmth is eroding it, peeling it away, revealing layers that have been hidden for eons. In a sense, we are watching an archaeological dig conducted by starlight, each layer that is exposed telling us something about a different epoch, a different set of conditions. And underneath, somewhere, is the core of 3I Atlas, the material that condensed from the disk around its parent star, relatively unprocessed, carrying the original chemical signature of that system. We have not reached that core yet. We are still observing the processed layers, the rind. But as 3I Atlas draws closer to perihelion, as the activity intensifies, we may yet catch a glimpse of what lies beneath. This is the promise of objects like 3I Atlas. They are not just interesting in themselves, though they are certainly that. They are windows into other worlds, other systems, other histories. Each one is a data point in the grand survey of how planets and stars and chemistry work across the galaxy. And as we accumulate more of these data points, as we detect more interstellar visitors, as we study them in greater detail, we will begin to see patterns, to understand variations, to answer questions about the diversity and unity of the cosmos that we cannot answer any other way. For now, though, we have just 3 such objects, and each one is precious, each one unique. 3I Atlas, with its deep negative polarization and its color transition and its mysterious composition, stands as a reminder that the universe is full of surprises, full of phenomena that do not fit neatly into our categories. And that is, perhaps, as it should be. A universe that yielded all its secrets easily, that confirmed all our expectations, would be a less interesting place. The mysteries, the anomalies, the things that do not quite make sense. These are not failures of understanding. They are invitations to look deeper, to think more carefully, to remain humble before the vastness and complexity of what we are trying to comprehend. Rest now, if sleep is calling. The polarized light will still be there tomorrow, still carrying its secrets, and we will still be here, watching, measuring, wondering. We have explored the surface of 3I Atlas, that ancient processed rind carrying the marks of a billion-year journey. Now, as you settle deeper into this quiet hour, we turn our attention to the path itself, to the trajectory this visitor has traced through our solar system, and what that path might tell us about where it has been and where it is going. There is a geometry to motion, a mathematics of gravity, and within those equations lie stories that span not just our solar system, but the galaxy beyond. Perhaps the weight of comfort is settling over you now, that gentle heaviness that precedes sleep. That's as it should be. Let your thoughts drift alongside 3I Atlas, following its curve through space. Feeling no urgency, no need to grasp at details, the universe moves at its own pace, and we can move with it, slowly, contemplatively. When an object enters our solar system from interstellar space, its path is determined by 2 primary factors: the velocity it carries from its galactic journey, and the gravitational pull of our Sun. These combine to create what mathematicians call a hyperbolic trajectory, a path that approaches from infinity, curves around the Sun, and returns to infinity, never closing, never repeating. It is the orbit of a visitor, not a resident, and the precise shape of that hyperbola, the angles at which it enters and exits our system, carries information about the object's origins and the forces that have shaped its journey. For 3I Atlas, that trajectory has revealed something immediately striking. The plane of its orbit, the imaginary flat surface that contains its path through space, is tilted only about 5 degrees from the ecliptic, that fundamental plane defined by Earth's orbit around the Sun. Think about what that means for a moment. The ecliptic is not arbitrary. It represents the plane of the solar system's formation, the flat disk of gas and dust from which the planets condensed. Objects born in our system naturally orbit close to this plane, with some scatter, but rarely more than a few degrees for the major planets, perhaps 30 degrees for more eccentric objects in the outer system. But 3I Atlas did not form here. It came from interstellar space, where there is no preferred plane, no natural alignment with our solar system's architecture. The galaxy itself has structure. The Milky Way is a flattened disk, but on the scale of stellar neighbourhoods, on the scale of the few light years that separate us from nearby stars, the orientations of planetary systems are essentially random. An object ejected from a random planetary system and travelling through the galaxy for eons should arrive at our solar system from a random direction, with no particular alignment to our ecliptic. Yet here is 3i Atlas, aligned to within 5 degrees. The probability of this happening by pure chance can be calculated, and it comes out to about 0.2%. Not impossible, not even terribly unlikely, if you consider that we might detect hundreds or thousands of interstellar objects over the coming decades, but unlikely enough to notice. Unlikely enough to wonder whether there is something about the geometry of interstellar space in our neighbourhood, or something about how objects enter the solar system, that might favour ecliptic-aligned trajectories. One explanation involves the structure of the heliosphere itself, that bubble carved out by the solar wind in the interstellar medium. The heliosphere is not spherical. It is elongated, shaped by the flow of interstellar gas past our solar system as we move through the galaxy. Objects approaching from certain directions might be channeled, their paths subtly bent by the magnetic fields and pressure gradients at the heliosphere's boundary. If such channeling favours trajectories aligned with the ecliptic, it could explain what we observe. But this is speculative, difficult to model precisely, and requires more observations of more interstellar objects to confirm or refute. Another possibility is that we are simply seeing a selection effect, a bias in what we detect. Our surveys for asteroids and comets are optimized to find objects near the ecliptic, because that is where the threats to Earth are most likely to come from. We scan the ecliptic more thoroughly, with more sensitive instruments, more frequently. An interstellar object arriving at a steep angle to the ecliptic might be missed, or detected only briefly before it passes beyond the range of our telescopes. If this is true, then 3i Atlas's alignment is not a property of interstellar objects in general, but a property of which interstellar objects we are capable of detecting. The universe is full of objects we do not see, and understanding our blind spots is as important as understanding what we do see. As you rest here, imagine the path of 3i Atlas traced through space, a curve drawn across the solar system over months and years. It entered from the direction of the constellation Ursa Major, the Great Bear, approaching from beyond Neptune's orbit, accelerating as the Sun's gravity took hold. By the time we detected it in July of 2025, it was already well within the orbit of Jupiter, moving at 58 kilometers per second, a speed that speaks of origins far from our Sun's warmth. That speed deserves a moment of reflection. For an object to be moving so fast relative to the Sun, it must have escaped not only its parent star's gravity, but also carried significant velocity from its motion through the galaxy. Stars in our neighbourhood move relative to one another at speeds of tens of kilometers per second, reflecting the random motions inherited from the Milky Way's formation and evolution. When a planetary system ejects an object, that object carries with it the orbital velocity it had around its planet, plus whatever boost the ejection itself provided, plus the velocity of the parent star through the galaxy. The resulting speed, when measured relative to a different star like our Sun, can be quite high, but 58 kilometers per second is at the upper end of what we expect for such objects, suggesting either a particularly violent ejection or a parent system with unusually high galactic velocity. In early October, 3i Atlas reached a milestone in its journey through our system. On October 3rd, it passed within 0.25 astronomical units of Mars, a distance of about 37 million kilometers. In the vastness of space, this is close. Close enough that the spacecraft and rovers we have stationed at Mars could potentially observe this visitor, instruments designed for other purposes briefly repurposed to study an interstellar traveller. Picture the view from Mars on that day. The sky, tinted butterscotch by the fine dust suspended in the thin Martian atmosphere, would host a faint but perceptible glow. Not bright enough to cast shadows, not obvious to a casual glance, but there, distinct against the stars. To a rover on the surface, perhaps one of the hardy machines we have sent to explore that world. 3i Atlas would appear as a diffuse patch of light, greenish if the rover's cameras were sensitive enough to capture the C2 emission, surrounded by the faint haze of its coma. The Mars Reconnaissance Orbiter, circling high above, might have captured images with enough resolution to glimpse the nucleus, that solid core at the heart of the comet, measuring its size, refining our estimates of its mass. But Mars, though the closest planetary encounter, is not the only gravitational influence on 3I Atlas's path. Jupiter, the giant of our solar system, exerts a pull that, while subtle, is measurable. As 3I Atlas curves through the inner system, approaching perihelion on October 31st, it will pass within a few astronomical units of Jupiter's orbit. Not close enough for a dramatic encounter, but close enough for Jupiter's gravity to slightly alter its trajectory. The change will be small, a fraction of a degree in direction, a tiny adjustment in velocity, but it will be real, and it will affect where 3I Atlas goes next. If you find this sort of calm exploration soothing, I'd be grateful if you gave the video a like, or maybe subscribed. It's a small gesture, but it helps more than it looks. It helps this quiet space reach others who might also enjoy wandering through these questions, who find comfort in contemplating the slow movements of the cosmos. I'm not asking because numbers matter here in the way they do in most places. I'm asking because the more people who join in, the richer these conversations can get. Sometimes it's the smallest comment, from someone in a completely different part of the world, that changes how you think about something. So if this resonates with you, if you find yourself returning to these kinds of explorations, consider subscribing. It means you'll be here when we turn our attention to the next mystery, the next visitor, the next question that the universe offers up. The gravitational dance between 3I Atlas and the planets is part of a broader story about how small objects move through the solar system. Every planet, every moon, every asteroid exerts a gravitational pull, and while most of these are negligible for an object moving as fast as 3I Atlas, they are not zero. Summed together, they represent a kind of gravitational weather, a complex field through which our visitor must navigate. And within that field, Jupiter stands out, its mass 318 times that of Earth, its influence extending far beyond its physical size. The effect of Jupiter on interstellar objects has been studied theoretically. In principle, Jupiter could capture an interstellar visitor, bend its trajectory enough to turn a hyperbolic orbit into an elliptical one, binding the object to our Sun. This requires a very specific geometry, a precise balance of velocity, distance, and angle, such that the object loses enough energy in the encounter to drop below escape velocity. For 3I Atlas, with its high incoming speed and its trajectory several degrees off the ecliptic, capture is not expected. But the thought experiment is instructive. It reminds us that the solar system is not sealed, that it breathes, exhaling comets from the Oort cloud, and occasionally inhaling visitors from the interstellar depths. If not this one, perhaps another, in some future generation, will be gentled into orbit by Jupiter's hand, and for a time, our Sun will borrow a comet born around another star. Recent work has attempted to trace 3I Atlas's trajectory backward in time, to identify where it came from before entering our solar system. This is a difficult problem, made harder by the fact that the positions and velocities of the stars are themselves uncertain. The Gaia Space Telescope, which has measured the positions and motions of over 1 billion stars with unprecedented precision, provides a database against which such questions can be tested. By integrating the orbit of 3I Atlas backward through the galaxy, accounting for the gravitational pull of the Milky Way's stars and dark matter, researchers can identify which stars 3I Atlas might have passed near in its history. The results are ambiguous. There are candidate encounters, stars that 3I Atlas might have approached within a few light years, but none that stand out as a clear origin. The closest encounter identified so far involves a wide binary system of M-dwarf stars, red dwarfs smaller and cooler than our Sun. The barycenter of this system, the point around which both stars orbit, and 3I Atlas would have approached within about 0.24 parsecs, roughly 50,000 astronomical units, about 1.6 million years ago. At that distance, the gravitational influence would have been modest, enough to slightly deflect 3I Atlas's path, but not enough to explain its current velocity or trajectory. Moreover, the relative velocity of that encounter, nearly 30 kilometers per second, is too high for the binary to be a plausible parent system. When objects are ejected from planetary systems, they typically leave with velocities relative to their parent star of a few kilometers per second, perhaps 10 or 20 at most, if the ejection is particularly violent. An encounter with a relative velocity of 30 kilometers per second suggests that 3I Atlas and the binary were not gravitationally bound, that they were ships passing in the night, each on its own trajectory through the galaxy. What this tells us is that 3I Atlas's origin remains uncertain. It might have been ejected from its parent system billions of years ago, so long ago that the star it once orbited has moved far from its current position, lost among the hundreds of billions of stars in the Milky Way, or it might have been ejected more recently, from a star that Gaia has not yet catalogued, a star too faint or too distant for our surveys to have captured. The galaxy is vast, and our knowledge, while growing, is still incomplete. But the analysis has revealed something else, something about the population of interstellar objects in general. The encounter rate, the frequency with which objects like 3I Atlas pass through the inner solar system, can be estimated from our detections and from the volume of space our surveys cover. Those estimates suggest that interstellar objects of this size, kilometre scale or larger, pass within Jupiter's orbit perhaps once per year, maybe more. Most go undetected, too faint or at the wrong angle for our telescopes to catch. We have seen 3 in the past 8 years, a rate that fits within these predictions, but also suggests that our surveys are only scratching the surface of what is out there. As 3I Atlas continues toward perihelion, as it draws closer to our Sun than it has been in perhaps 1 billion years, the activity will intensify, more ice will sublimate, more dust will be released, the coma will grow brighter and larger, and with that increased activity comes increased opportunity to study this visitor, to measure properties that are only revealed under the stress of solar heating. Spectroscopic observations will become more detailed, capturing emission lines from molecules that are present in trace amounts, too faint to detect earlier. Imaging will resolve structure within the coma, jets and streamers that tell us about the rotation and surface heterogeneity of the nucleus. There is something poignant about this intensification, a recognition that it is temporary. After perihelion, 3I Atlas will begin the outward leg of its journey, receding from the Sun, cooling, the activity gradually diminishing until eventually it goes dormant again, a frozen wanderer heading back into the dark. We will watch it for as long as we can, tracking it with increasingly large telescopes as it fades, extracting every bit of information possible, but eventually it will be too faint, too distant, and we will lose sight of it. It will return to being what it was before we detected it, an anonymous traveller in the galaxy, one among billions, carrying its secrets onward through the cosmos. The trajectory of 3I Atlas also speaks to the dynamical history of the galaxy itself. Interstellar objects are not just passively drifting. They are part of the galactic ecosystem, a component of the matter that moves between stars, subject to the same gravitational perturbations that shape the orbits of stars and gas clouds. Over billions of years, an object like 3I Atlas will have its trajectory altered by countless close passes to stars, by the gentle tug of the galaxy's spiral arms, by the passage through regions of varying density. It is, in a very real sense, a probe of the galactic environment, a test particle whose orbit integrates the gravitational history of its journey. Simulations of interstellar object populations suggest that most such objects, after being ejected from their parent systems, remain in roughly the same region of the galaxy where they were born. They drift slowly relative to nearby stars, occasionally encountering another stellar system, but mostly travelling through the empty space between stars. Over time, their distribution tends to match the distribution of stars themselves, concentrated in the galactic plane thinning out above and below. The fact that 3I Atlas has arrived at our solar system suggests, statistically, that it likely originated relatively nearby, within a few hundred light years perhaps, though nearby in this context is still a vast distance, thousands of times the size of our solar system. One particularly intriguing possibility raised by some researchers is that interstellar objects might serve as vectors for panspermia, the transfer of life or its precursors between planetary systems. If an object like 3I Atlas spent its early history on the edge of a habitable zone around another star, it might have collected organic material, perhaps even microbial life, before being ejected. During its interstellar journey, that material would be frozen, preserved in a kind of cryogenic stasis. If such an object were then captured by another planetary system, or if it delivered material through impacts or outgassing, it could, in principle, seed that system with the chemistry or biology of its origin. This is speculative, of course, far beyond what we can test with current observations of 3I Atlas, but it is not outside the realm of physical possibility. We know that some microorganisms can survive extreme cold, extreme radiation, for extended periods. We know that organic molecules are found throughout the galaxy, and we know that interstellar objects do occasionally pass through planetary systems, as 3I Atlas is doing now. Whether such transfers have actually occurred, whether life on Earth might have been influenced by material delivered from another star, these are open questions, part of the larger puzzle of how life arises and spreads through the cosmos. As you drift now, perhaps close to sleep, picture 3I Atlas as a thread in the vast tapestry of the galaxy. One line among billions, crossing and recrossing, weaving a pattern that spans light years and eons. Each star system is a node in that tapestry, occasionally shedding objects that become new threads, occasionally capturing objects whose threads began elsewhere. And we, in our solar system, are part of that pattern, connected to the broader galaxy in ways both material and informational, receiving visitors like 3I Atlas that bring news of other places, other times. The trajectory will carry 3I Atlas out of our system over the coming months and years. It will cross back out beyond Jupiter's orbit, beyond Saturn, Neptune, into the Kuiper Belt, and eventually the Oort cloud, those distant regions where the sun's influence fades and the cold of interstellar space reasserts itself. And then, once more, it will be alone, travelling through the dark, its surface modified by this brief encounter with warmth, carrying those modifications as a kind of memory, a record of having passed close to a star. Perhaps, in another million years, it will encounter another system. Perhaps not. The galaxy is large, and stars are far apart. But the possibility exists, and in that possibility is a kind of immortality, a sense that this fragment of rock and ice born around one star will continue its journey indefinitely, touching different systems, accumulating history, a silent witness to the slow evolution of the galaxy itself. For now, though, it is here, in our system, and we are watching. That is enough. That is more than enough. We have travelled alongside 3I Atlas through discovery, anomaly, composition, and trajectory. Now, as you rest in whatever quiet holds you, we turn to a different kind of question, one that moves from observation to meaning, from measurement to implication. What does it mean that this object exists? What does it tell us about the universe, about the processes that shape matter and motion across the galaxy? And how do we, as a civilization, respond when confronted with something that challenges the boundaries of our understanding? Perhaps sleep is close now, hovering just at the edge of your awareness. That's good, let it come as it will. We are nearing the end of this journey, and these final questions are meant to settle gently, to rest in the mind without demanding resolution. In late September of 2025, as the data from 3I Atlas accumulated and the peculiarities became undeniable, a document was submitted to the United Nations. This was not a scientific paper in the traditional sense, not a peer-reviewed article for a journal, but rather a white paper, a policy document arguing for coordinated international response to interstellar objects. The authors, a group of researchers spanning multiple institutions and countries, made a careful argument. They acknowledged the uncertainties, the multiple possible interpretations of the observations, but they also noted that if there is even a small possibility that interstellar objects could carry information about extraterrestrial technology, that possibility deserves serious, systematic study. Not because it is likely, but because the implications, if true, would be profound. This is a kind of reasoning that appears in various contexts, sometimes called Pascal's wager when applied to questions of existence and belief. The idea is straightforward. If the probability of an event is small, but the consequence of that event is enormous, the expected value of investigating it may be large even if the probability is tiny. For interstellar objects, the argument goes, even a 1 in a million chance that an object like 3I Atlas carries artificial signatures is worth taking seriously, because discovering such signatures would fundamentally alter our understanding of our place in the cosmos. The response came 3 weeks later. On October 21st, the International Asteroid Warning Network, a body operating under United Nations auspices and responsible for coordinating observations of potentially hazardous asteroids, announced a campaign specifically targeting 3I Atlas. The campaign would run from late November 2025 through late January 2026, spanning the period when 3I Atlas would be near perihelion and at its brightest. The stated goal was to improve astrometric measurements of cometary bodies to better understand how the diffuse coma and tail affect position measurements, a problem relevant not just for interstellar visitors, but for any comet that might someday pose a threat. But the announcement included something unusual. Participation in the campaign required attendance at a workshop. Registration had to be completed by early November. Only those who attended the workshop could contribute observations. In an era of citizen science, where amateur astronomers regularly contribute valuable data to professional research, this was a controlled protocol, a standardized approach that ensured consistency, but also limited who could participate. It spoke to the seriousness with which the observations were being taken, the recognition that what we learn from 3I Atlas might shape how we think about interstellar objects for years to come. What were they looking for, these coordinated observers? Officially, the goal was astrometric precision, measuring the exact position of 3I Atlas's nucleus as it moved across the sky, refining our knowledge of its orbit. But astrometry, done carefully, can reveal more than just position. Small deviations from a purely gravitational trajectory, non-gravitational accelerations caused by outgassing or other forces, leave signatures in the positional data. If the outgassing is symmetric, if the forces average out, the trajectory might appear purely gravitational. But if there are asymmetries, if jets are preferentially directed in certain directions, the trajectory will deviate in measurable ways. Such deviations are common in comets from our solar system. They are well studied, understood as the natural consequence of sublimation creating rocket-like thrust. For 3I Atlas, measuring such effects would tell us about the distribution of active regions on the nucleus, about the rotation, about how the interior responds to solar heating, but it would also, in principle, allow us to rule out or constrain other possibilities, explanations that involve directed forces of non-natural origin. This is the subtext beneath the official statements, the unspoken question that hovers around observations of any interstellar object that behaves unexpectedly. As you rest here, imagine the network of telescopes turning their attention to this single point of light. Observers scattered across the globe, each contributing measurements, each adding to the collective understanding. There is something beautiful in that coordination, in the recognition that some questions are too large for any single observatory or nation to answer alone. The universe does not respect political boundaries, and neither does the pursuit of knowledge. The analysis of 3I Atlas's galactic origin has continued in parallel with these observational campaigns. Recent work, combining the trajectory data with models of stellar populations in the Milky Way, suggests that 3I Atlas most likely originated in what astronomers call the thin disk of the galaxy. This is the flat rotating component where most stars and gas reside, including our Sun. Objects ejected from planetary systems in the thin disk would naturally have velocities that reflect the disk's rotation, and when such objects encounter our solar system, their trajectories would show certain characteristics, certain biases in direction and speed. The velocity of 3I Atlas, when corrected for the Sun's own motion through the galaxy, fits well with the velocity distribution expected for thin disk objects. This does not tell us which specific star it came from. The thin disk contains hundreds of billions of stars, but it does tell us something about the type of environment where 3I Atlas likely formed. A thin disk origin suggests a star similar to our Sun in age and composition, a planetary system where Earth-like conditions might plausibly exist. It is a reminder that 3I Atlas is not some exotic relic from the galaxy's ancient past, or its metal-poor halo, but rather a product of the same stellar generation that includes our own star. This statistical preference for thin disk origins applies not just to 3I Atlas, but to interstellar objects in general. If most interstellar visitors come from the thin disk, it is because the thin disk dominates the local stellar density. We are, after all, embedded in the thin disk ourselves. The stars we see in the night sky, with few exceptions, are thin disk stars. It makes sense that most of the objects wandering between stars in our neighbourhood would also originate there. But this recognition does not diminish the wonder. It situates 3I Atlas within a broader context, connects it to the galactic ecosystem, makes it part of a story that includes our own solar system's formation and evolution. There is also the question of how long 3I Atlas has been travelling. If we could measure its trajectory with infinite precision, if we could account for every gravitational perturbation it has experienced, we might be able to trace its path all the way back to its birth system. In practice, the uncertainties accumulate, and the further back we try to integrate the orbit, the larger the volume of space where the origin could lie. Current estimates suggest that 3I Atlas has been travelling for at least tens of millions of years, possibly much longer. The surface processing we observe, the cosmic ray exposure, the deep alteration of the outer layers, all point to timescales measured in hundreds of millions to billions of years. But the exact number remains uncertain, a reminder that time, like distance, becomes fuzzy when we look deep into the past. What happens to an object during such a journey? We have touched on this earlier, but it bears reflection. For millions, or billions, of years, 3I Atlas drifted through interstellar space, bombarded by cosmic rays, exposed to the faint starlight of the galaxy, its surface temperature held at just a few degrees above absolute zero by the cosmic microwave background. During that time, chemistry happened, slowly, driven by the energy deposited by cosmic ray impacts. Simple molecules were broken apart. Radicals wandered through the ice, occasionally finding each other and forming more complex structures. The surface darkened as volatile ices were preferentially removed, leaving behind a lag deposit of dust and organics. And then, perhaps just a few million years ago, a blink in the context of its full journey, 3I Atlas's trajectory began to bend as it entered the gravitational sphere of our Sun. The change was gradual at first, imperceptible against the backdrop of galactic motion. But as the distance closed, the bending became more pronounced, the trajectory more sharply curved, until 3I Atlas was committed to this passage. This brief encounter with warmth and light after eons of cold and dark. The surface began to respond, the ices near the surface warming just enough to begin sublimating, the coma forming, the transformation from inert rock to active comet beginning. We are witnessing the reawakening of an object that has been dormant longer than complex life has existed on Earth. When 3I Atlas was ejected from its birth system, Earth's biosphere might have consisted of nothing more than single-celled organisms, perhaps not even eukaryotes, no plants, no animals, no consciousness. And now, as 3I Atlas passes through our system, it encounters a world teeming with life, a species that has developed technology, built telescopes and turned them toward the sky to study visitors from other stars. There is an asymmetry here, a poignancy in the recognition that 3I Atlas carries no knowledge of us, no awareness that it is being observed, while we pour attention and resources into understanding it. But perhaps that asymmetry is temporary, in some broader sense. If other civilizations exist in the galaxy, if some have reached the point where they too build telescopes and study interstellar objects, then perhaps 3I Atlas has been observed before, by minds very different from ours, around a different star at a different time, and perhaps it will be observed again in the distant future, after it leaves our system and continues its galactic journey, encountering some other stellar system where curious beings wonder at its composition and trajectory. In that way, 3I Atlas becomes a kind of shared experience, a common reference point for anyone in the galaxy who has reached the stage of astronomical observation. This is speculative, of course, edging into philosophy more than science, but it is worth considering, especially as we think about the implications of detecting more and more interstellar objects. Each one is a messenger, carrying information about the galaxy's structure, its chemistry, its dynamical history, and if we listen carefully, if we measure precisely, we might begin to hear patterns, to understand not just individual objects, but the population as a whole, the distribution of compositions and velocities and trajectories that tells us about planet formation and stellar evolution across the galaxy. The controlled observation campaign for 3i Atlas, with its workshop requirement and standardized protocols, reflects a maturation of the field. When Oumuamua was detected, it was a surprise, and the response was somewhat chaotic, with different groups measuring different things in different ways. By the time 2i Borisov arrived, there was more coordination, but still much variation in how observations were conducted. Now, with 3i Atlas, there is an attempt at systematic study, at ensuring that the data collected can be compared and combined, that we extract maximum information from this opportunity. This is how science progresses, not just through individual insights, but through the development of methods, standards, infrastructure that allows knowledge to accumulate reliably, as you drift now, perhaps on the very edge of sleep. Consider the layers of response that an object like 3i Atlas provokes. There is the immediate response of astronomers, pointing telescopes, gathering data, trying to understand what they are seeing. There is the broader scientific community, debating interpretations, constructing models, testing hypotheses. There is the policy level, the United Nations and international organizations trying to coordinate and sometimes to manage public expectations. And there is the public itself, learning about these discoveries through news articles and documentaries, forming their own ideas about what it means. Each of these layers operates on different timescales with different priorities, but they're all part of the same process, the collective attempt to make sense of something new. And the questions raised by 3i Atlas about its composition, its trajectory, its anomalies, these questions ripple through all those layers, prompting discussions that range from the highly technical to the deeply philosophical. In the end, what 3i Atlas implies might depend as much on what we bring to the observation as on what the object itself is. If we approach it expecting to find only natural phenomena, we will interpret the data through that lens, finding explanations within known physics, even when those explanations require unlikely combinations of circumstances. If we approach it open to the possibility of something more, we might see hints and suggestions in the data that others dismiss as noise or artifact. Neither approach is wrong exactly. They represent different weightings of probabilities, different judgments about when to accept the conventional and when to seriously consider the unconventional. What the scientific method demands is not that we close off possibilities, but that we proportion our confidence to the evidence, that we remain open to revision as more data comes in, and that we distinguish carefully between what we know and what we speculate. For 3i Atlas, we know its trajectory, its spectrum, its polarization, its brightening curve. We know the statistical improbabilities associated with some of its properties. What we do not know, not yet, is the full story of how it came to be what it is, whether the anomalies arise from natural processes we have not yet fully understood, or from something else. That uncertainty is not a failure. It is the space where discovery happens, where new understanding emerges. And as we watch 3i Atlas continue its journey through our system, as we gather more data and refine our models, that space of uncertainty will narrow, and we will move closer to answers. Perhaps not complete answers, perhaps not the dramatic revelations that some hope for, but incremental progress, the slow accretion of knowledge that characterizes all deep inquiry into the nature of things. Rest now if sleep is calling. The questions will still be there tomorrow, and the universe will still be speaking, in its patient, photon-by-photon way, to those who listen. We have wandered through the story of 3i Atlas for a while now, from its first detection in the summer sky, to the accumulating evidence of its strangeness, from the composition of its ancient surface to the trajectory that brought it here, and the questions that its presence raises. Now, as you rest on the edge of sleep, we come to the place where all such explorations must end, not with answers, but with the acknowledgement that the universe keeps its mysteries close, revealing them slowly, if at all. Perhaps you're already drifting, thoughts dissolving into the formless space that precedes dreams. That is as it should be. Let these final reflections settle gently, without weight, without demand. As October gave way to November, as 3i Atlas approached and then passed through perihelion on October 31st, the observations continued. Telescopes tracked its brightening, measured the expansion of its coma, recorded the subtle shifts in its spectrum as different ices sublimated at different rates. The nucleus, that solid core at the heart of all this activity, remained elusive, hidden within the glowing haze of gas and dust. Estimates of its size, based on how much sunlight it reflects and how much material it produces, suggest something between a few hundred meters and perhaps a few kilometers across. Small by planetary standards, but substantial enough to carry. Within it, a record of its formation and history. After perihelion, as Earth's geometry improved and the sun's glare diminished, observers resumed their patient work. They looked for changes in the activity, for signs that the comet was settling back to a quieter state, or continuing to surprise with new outbursts. They measured colours, watching to see if the green of carbon dimer emission remained strong, or if other molecules began to dominate the spectrum. They searched for ion tails, those narrow straight features shaped by magnetic fields, which sometimes become more prominent as the neutral gas production wanes, and they refined the orbital calculations, ingesting each new measurement of position, adding non-gravitational terms to account for the rocket effect of outgassing, watching those terms evolve as the activity changed. Each data point, each measurement, narrowed the space of possibilities slightly. The trajectory became more precisely known, the outbound path more clearly defined. By early 2026, it will be possible to predict where 3i Atlas will be decades from now, centuries from now, as it recedes from our Sun and returns to the interstellar medium. The encounter with Jupiter, that subtle gravitational interaction we discussed, will have imparted a small change in velocity, a fraction of a meter per second perhaps, but enough to alter the future path measurably. 3i Atlas will leave our system slightly different than it arrived, carrying the mark of this passage in its trajectory. But the physical changes are perhaps more profound. The surface of 3i Atlas, processed by solar heating for the first time in eons, will be different. The red, organic-rich crust that covered it upon arrival has been at least partially removed, sublimated away, or blown off by the pressure of escaping gas. Fresher material, less irradiated, less altered by cosmic rays, has been exposed. This fresher material will itself begin to be processed as 3i Atlas returns to interstellar space, as cosmic rays once again become the dominant form of energy input. Over millions of years, new crust will form, and the memory of this solar encounter will be buried beneath it, detectable perhaps only through careful analysis of isotopic ratios or the structure of complex organics. In this way, 3i Atlas will carry a record of us, or at least of our Sun, even if it carries no knowledge of our civilization. The photons that struck its surface, the solar wind that swept over its coma, these left traces, subtle alterations in chemistry and structure. If in some distant future 3i Atlas is captured by another star, and if beings around that star develop the technology to study it closely, they might find those traces and wonder about the star that warmed it briefly, billions of years in their past. There is comfort in that thought, perhaps, a sense of connection across time and space that does not require communication or even awareness. We touch the universe simply by existing, by the gravitational pull we exert, by the light we emit, by the objects that pass through our neighbourhood and carry away some record of the encounter. And the universe touches us in return, through objects like 3i Atlas, through the photons they send our way, through the questions they provoke. The question that lingers, the one that perhaps cannot be fully answered with current data, is whether 3i Atlas is entirely natural, or whether some of its features hint at something more. The statistical improbabilities, the combination of anomalies, these invite consideration of alternatives. But alternatives require evidence beyond statistical unlikelihood. They require mechanisms, predictions, observations that distinguish between hypotheses. For now, we have observations that are surprising but not inexplicable, unusual but not impossible. The space for extraordinary explanations remains, but it is constrained by the same data that reveals the anomalies in the first place. This is how it should be. Science does not leap to conclusions. It builds understanding slowly, testing each step, remaining open to revision, but demanding rigor. The story of 3i Atlas is not finished. More observations will be made, more papers will be written, more models will be constructed and tested, and with each iteration our understanding will deepen, the picture will clarify, even if some questions remain unanswered. As you lie here now, carried perhaps fully into sleep, let the image of 3i Atlas rest in your mind, a small dark object, glowing faintly green from the carbon molecules breaking apart in its coma, racing outward from the sun, leaving our system behind. It does not know we watched it. It carries no message, no intention, only the mute testimony of its composition and motion. But in that testimony, we find connection, a thread linking us to other places, other times, other possibilities. The mystery remains, and perhaps that is fitting. Perhaps the questions themselves are what matter. The invitation to look more carefully, to think more deeply, to remain humble before the vastness of what we do not yet understand. The universe rewards that attention with clarity when it can, with mystery when it must. And in the balance between knowing and not knowing, we find the space where wonder lives. We have wandered through the story of 3i Atlas together, exploring its discovery, its anomalies, its composition, its trajectory, and the implications of its existence. The question remains, what is this object? Where did it come from? Why does it behave the way it does? We have partial answers, pieces of the puzzle, but the full picture eludes us still. Perhaps that is fitting. Perhaps the questions themselves are the gift, the reminder that the universe is richer and stranger than we imagined. For now, let this thought sit with you as you drift towards sleep. Somewhere out there, beyond the reach of sunlight, 3i Atlas continues its journey. The stars it will pass in the coming millennia have not yet risen above our horizon. The systems it might visit are unknown to us. But the journey continues, patient and unhurried, as it has for eons, as it will for eons more. Thank you for wandering through this cosmic question with me tonight. Thank you for bringing your attention, your curiosity, your willingness to sit with uncertainty. Wherever you are, whatever space holds you in this moment, I hope you find rest. I hope the questions we have explored settle into something like peace, not demanding resolution, but simply being, present and patient, like the stars themselves. The universe will still be here tomorrow, still speaking in its language of light and motion, still offering mysteries for those who wish to listen, and we will still be here, watching, wondering, learning what we can from the travellers that pass our way. Sleep well. The cosmos keeps its vigil, and so do we, each in our own way, under the same vast sky.